Let's talk about curvilinear motion, but let's specifically talk about rectangular components. And you've dealt with these a lot in statics before, so this should be a pretty easy review. Here's our standard coordinate system, x, y, z, with z going up. And let's say we have a particle going along some path. We can define the position of that particle at any time by drawing a position vector r. And in this case, with rectangular coordinates, we're going to get some amount in the I direction, or the x, some amount in the y or j direction, and some amount in the k direction. Now, we're going to do almost primarily two-dimensional problems in this class, but if you remember, when you take cross products of 2 dimensions, you get that third dimension. So we will be dealing with 3 dimensions, but most of the stuff we do will be in 2 dimensions. The third dimension is just another dimension, just makes the problem a little bit harder. Okay, so if we have that position vector, we can find out what the magnitude is by taking the square root of the x component squared plus the y component squared plus the z component. And if there's no z component, right, just don't put it in there. If we wanted a unit vector in the direction of r, we would have to take r and divide it by the magnitude of r. Right? A unit vector is something that is one long, but in the direction of the vector you're talking about. Okay, so the next step would be taking the time derivative of this. You're going to catch on to that. The next step is typically calculus. Take the time derivative, and what do we get? We get the velocity. It's equal to the time derivative of the x component plus the time derivative of the y component plus the time derivative of the z or k component. We can then say that the velocity is equal to dr dt, and it has some velocity in the x direction, some velocity in the y direction, and possibly also some velocity in the z direction. Alright, so that we need these. That was also important. This was important. This was important. That should all be reviewed though, except for maybe the velocity part. But all we did is take the time derivative. Now I'm going to take the time to introduce new notation. This you probably have not seen before. Alright, I'm going to call this thing, the velocity in the x direction, x dot, where the dot means time derivative. So in this case, that's the time derivative of position, right? dr dt. That gives us the velocity. So we can say the velocity in the y direction is equal to y dot, and the velocity in the z direction is equal to z dot. We'll take that one step further in a second, and don't forget, we can always find the magnitude of any vector if we take the square root of its components. We got the velocity in the x direction squared plus the velocity in the y squared plus the velocity in the z squared, and the unit vector the same way. Let's take another derivative. Oh, take one more derivative. That's usually the answer. And what do we get? The derivative of velocity with respect to time is acceleration. And we get, just like velocity, some x component of acceleration, some y component of acceleration, and some z component of acceleration. So we need that, and then we also need to do the same thing with this notation, the new notation. I'm going to call the acceleration in the x direction now the time derivative of velocity. So v dot x. Now the time derivative of velocity is equal to the second derivative of position, so I can say double dot on top of that x. These are all equal, and then we can do that for y also. The acceleration is equal to v dot or y double dot. The acceleration in the z is equal to v of z dot, and it's also equal to z double dot. So 2 dots equals 2 time derivatives. Okay, and once again we can find the magnitude if we take the square root of the following. Okay, now that we have those, I'm going to do a quick little review. Let's say we had, just an example problem. Let's say we have, and I think this is 12.6 on page 49. I'm jumping ahead a little bit, but I feel like it fits in here well. They put it in with projectile motion for some reason, and it has nothing to do with that. They give us the velocity as a function of time, and they say it is equal to 16t squared in the I direction. You can put parentheses around there if you want, plus 4t to the third, and that's the j direction component. And we have 5t plus 2, and that's in the k direction. And that is all in meters per second. Don't forget your units, very important. Then they give us the fact that at t is equal to 0, the position is at the origin. It has not moved. They want us to find the magnitude of the acceleration at t is equal to 2 seconds, and they want us to find the x, y, z coordinate, its position at 2 seconds. Alright, let's do it. So we learned that the acceleration is equal to the time derivative of velocity. So let's do that for each component. The acceleration will be equal to, if I take the derivative of 16t squared, I get 32t, and that's in the I direction. Hold on to the direction. If I take the derivative of the j, I get 12t squared, and that's in the j direction. And if I take the derivative of the k component, I just get a 5. And don't forget the k hat. That all is in meters per second squared, and if we evaluated that at t is equal to 2 seconds, we would get our acceleration vector. To get the magnitude like they asked for, we would take the square root of whatever this is at 2 squared plus whatever this is at 2 squared plus 5 squared. Okay, so that would be your answer. What about the XYZ part? That's a little bit trickier. They want to know what position or what is the coordinate at 2 seconds. XYZ at 2 seconds. Well, we're going to go back the other way. I'm going to take each component. The x component, the velocity in the x direction, is this thing right there. The 3, what did I write? 32t. There we go. But I want this right here, the 16t squared. That is the x component of the velocity that they gave us. If I use the fact that the velocity is equal to dx dt, and then move dt over here with its other like term, we get an integrable equation. 16t squared dt. And we can integrate it from 0 to x final to find out where its position is, because they told us at t is equal to 0, its position is 0. And we can integrate the other side from 0 to 2. And we would do that for each component. So this one gives me a x as a function of time. That's 16/3 t to the third. Okay, so if I wanted to do that for the y coordinate, velocity in the y direction, I would take 4t to the third, do the same thing, dx, or sorry, let's use dy dt this time is equal to 4t to the third, move that over, dy is equal to 4t to the third dt, and now we can integrate. I get y at some t as, do it in my head, t to the fourth. Alright, and we can evaluate that at any t also. And what about the z? The velocity in the z direction was 5t plus 2. That was given at the beginning. That's equal to dz dt. Let's move the dt over, so I get dz is equal to 5t plus 2 dt. Then I would integrate again and get the z component as a function of time to be 5/2 t squared plus 2t. Alright, now we got to reconstruct it. They want to know the position at t is equal to 2 seconds. Well, we need to take this 16/3 to the third, and that's in the I direction. We need to take this t to the fourth in the j direction. And we have this one right here, 5/2 t squared plus 2t, and that's in the k direction. So that's a general function, and that would be in meters. If we plugged in any time t, we could get where the particle is. For this specific problem, they wanted t is equal to 2. You could just plug in 2 here, 2 here, 2 here, and 2 here to get that. Alright, thank you.